Yeah, very good. Okay.
Okay. So, as the people who came here before know, we have a tradition to always have one course devoted to part of physics itself, and in particular nowadays it's a very fortunate thing with lots of new data coming in from LHC here at CERN. But before I introduce the speaker, I want to remind you tomorrow morning we have a talk by an experimental physicist, Albert Beroep, from CERN and University of Antwerp. And contrary to the other days, tomorrow's session starts at 9 o'clock, so not 9:30, but 9 o'clock, half an hour earlier as usual. So now it's a pleasure to introduce Giudice from CERN, who will be giving us a series of lectures on beyond the standard model physics in light of LHC and TeV.
Good morning. Can you hear me? It's okay, the microphone. Thank you. So I was asked to talk about the status of BSM physics after the first run of the LHC. And I find myself in a slightly embarrassing situation because from the theoretical point of view, we have many ideas, and some of them are really fascinating. Changing the real fabric of space-time, introducing new kind of forces, introducing new space dimensions. And I think that the beauty and the power of some of these theories really goes beyond their motivation from the weak scale. Think of supersymmetry or some of the concept in extra dimensions and so on. But most of these ideas are not really new. Are physics, I would say physics of the past century, or maybe actually physics of the past millennium. So the new data is certainly changing our perspective, mostly constraining all these ideas, but the foundations of the idea, the conceptual part, really remains the same. From the experimental point of view, this is a glorious time, with the LHC completing the exploration of the TeV scale. And BSM physics is certainly the core of the LHC project, which is an exploratory machine for the new energy range. However, what new physics has been discovered by the LHC? Nothing. Of course, the LHC has discovered the Higgs. But from the point of view of new physics, a standard model Higgs is almost, I would say, a negative discovery. And certainly does not satisfy our appetite for understanding the dynamics of the electroweak breaking. And it leaves many problems unsolved. So I think we are really at a turning point in high-energy physics, and the next few years will determine the future of the field from the experimental side to the theoretical side, and even all the way to string theory, I would say. So given the uncertainty of this situation in the theoretical scene, what shall I talk about? And some years ago, in a previous edition of this school, I've talked about supersymmetric model building. But this year I felt that I didn't want to present such material. I don't want to show you models which then are going to be part of history, of the history of physics, probably very soon. And I don't want to show you plots and tables of limits of all these models. So I decided that I think that we'll postpone. We will talk about supersymmetry and extra dimension, or you name it, the year in which supersymmetry, extra dimension, and you name it, will be discovered. 2012 has been the year of the Higgs discovery, and so I took the liberty of changing the title of my lectures, and I will discuss mostly the Higgs. And I will discuss the meaning and the implication of the discovery, so please change the title. Sorry, Neil. I took this liberty, but I also promise that I'll try to do it with a BSM perspective in order not just to stop at the standard model, but trying to understand what are we really learning, because we think that the Higgs discovery was the first step towards some new understanding. So you're very familiar with the idea of spontaneous symmetry breaking, and the best realization is in a scalar theory. And once you define the vacuum state as the state of minimum energy, and you require that your theory is invariant under a linear transformation of the field, where T are the generators, then by taking the first derivative of this equation, the invariance equation, you find this, which, since on the vacuum we said that by definition this term is 0, and this second derivative on the vacuum is the mass square of the scalar fields, you find this famous result that for each broken generator, so for each generator which does not leave the vacuum invariant, so delta phi on the vacuum is different than 0, you find one massless state. Now, this is very useful as a starting point, because given that there are some massless states in the theory, I can use an effective theory valid below the typical mass scale of all the other scalars and describe just the Goldstone boson. This approach is very useful because it really describes the essence of the dynamics of spontaneous symmetry breaking without the need of specifying the full model of the theory. And it will be very useful for our discussion because we want to test the idea of electroweak symmetry breaking. So I don't want to start from the Higgs potential, but instead I want to see what is the most general theory from which I can get electroweak breaking, and then compare it to data. So data should not be compared just to the Higgs model, but with a general framework, and then see what is the result. So, as you know, there are two ways of realizing symmetries. One, which is so-called exact symmetry, in which the vacuum is invariant under a symmetry group G. And then the result is that the physical states come out in mass-degenerate multiplets. And all the fields transform linearly under my group transformation. The second possibility is that the vacuum leaves invariant only a subgroup H of G. And then in this case, we have a set of equivalent vacua related by symmetry transformation, by the symmetry transformation of the coset group of G divided by H. Now, in this case, the physical state form multiplets only of the subgroup H and not of G. And we have in the spectrum some massless Goldstone, one for each generator of G divided by H. And in this case, the fields transform non-linearly. But of course, in both cases, the symmetry is there in the sense that there are conserved currents. Now, this story becomes much more interesting once I make this symmetry local and not just global. Instead of just giving the general framework, let me just concentrate on the standard model, because this is what I have in mind. So my group G will be the SU2 times U1 gauge group, and the subgroup that I want to leave unbroken is U1 electromagnetism, so that this U1 is embedded in a non-trivial way, and the generator Q of the U1 is a linear combination of the diagonal generator of SU2 and the one of U1. Then let me start by constructing a field sigma in this way. I take the exponential of 3 fields chi times the Pauli matrix. And I divide this in order to obtain something dimensionless. This is a scalar field, so it's dimension 1, by 1 scale, which will be the scale of electroweak breaking. So since we know it from data that this is 246 GeV, I fix it to that value. The local symmetry gauge transformation of this field, the sigma, are defined by the product of a left matrix, of an SU2 matrix to the left and a U1 matrix to the right, where the SU2 and the U1 transformation are defined in this way, in a standard way. Now notice that if I assume that the field chi have 0 vacuum expectation value, then on the vacuum, this field sigma has a background value of 1, okay, because the chi's are 0. Now this vacuum here is left invariant, is not invariant under the full SU2 times U1 transformation, because you have different matrices acting on the left and the right, but it is invariant under a transformation in which these two matrices are the same, meaning that I have to choose a parameter transformation with lambda 1, lambda 2 equal to 0, and lambda 3, the 3 of, of here, okay, the lambda 3 is equal to lambda y. So that, I leave invariant because the product, the matrix that I multiply on the left and the right are exactly equal. So this vacuum realizes exactly the breaking of G into H, where G is SU2 times U1, H is electromagnetism. Notice also that this field sigma is such that if I take sigma dagger sigma, I get 1, meaning that I don't have any dynamical information in that product, so that we cannot write any non-derivative interaction invariant under G, because that would contain only products of sigma. In order to make invariant, I have to take the product, and does not contain the field. So that means that the field chi do not have a potential, they are massless, and so they describe exactly the 3 Goldstone bosons of G over H. Now, how do these fields transform? Well, this is a simple exercise. If you want, you can do it yourself. You just take the general transformation that I said, you expand this exponential in the field chi, taking these two matrices as the SU2 times and U1 transformation. And what you find is that once I expand the transformation properties in powers of fields, I find that the leading term is just a shift. So this is exactly the shift of the Goldstone boson as I expected. But also, I'm getting nonlinearity. So I'm getting that this field transforms nonlinearly in a complicated way. However, under the generator Q, remember the one which is left invariant by the vacuum, what you find is that, see, if I'm taking the delta 3 equal to delta y, these two terms exactly cancel, and actually all the nonlinearities cancel, and so I find that the fields transform linearly in that case, and they correspond to one neutral and one charge state. So you see that really I'm constructing exactly a specific Lagrangian describing the Goldstone bosons. Actually, one can prove a theorem showing that this field sigma gives a most general nonlinear representation of G. Okay, so now I have my degrees of freedom. I want to construct the Lagrangian. We've seen that sigma dagger sigma is 1, so I need to introduce derivatives. I have a local symmetry, so I have to introduce covariant derivatives of this field sigma, and this means that I have to introduce an SU2 gauge field, which are the W's, and a U1 hypercharge gauge field. My effective Lagrangian will be an expansion in powers of derivatives. This is a low-energy effective theory, valid at low momentum. So I'm taking this series, which gives a better and better description of my Lagrangian. So one can easily see that once I work at the lowest derivative level, two derivatives, I can write down two possible terms. One is this one. I mean, you can do it as an exercise by yourself. It's useful. If you have never seen it, this construction, this term you recognize. This is a canonical kinetic term, if you wish, for the field sigma. Notice that I always have to multiply by v, the scale, in order to get something that has the right dimensions. Sigma is a dimensionless field. So this is dimension 4 because there are two derivatives. But I also can construct another invariant at the level of two derivatives. And this is because I have a U1 transformation to the right, so I can construct something that multiplies by sigma 3. Very good. So now this is the most general Lagrangian, which is this one. And notice that on the vacuum that we assume to be sigma equal to 1, these two terms give me masses for the gauge fields. And this is immediate because when I set sigma equal to 1, what I'm picking here is not the derivative, but the gauge part, and these are bilinear in the gauge fields. So I'm getting one term for the charged gauge boson and one term for the neutral gauge boson. And this is the expression of these two masses in terms of these two operators. In the second one, I introduced just a coefficient, an arbitrary coefficient, CT. The normalization of this operator is fixed by requiring that the chi fields have a canonical gauge field, kinetic term. So notice that this is not the usual expression that you're familiar when you construct the Higgs model, because you have an extra term. If you go in unitary gauge, so the chi field are 0, what you discover is the well-known Higgs mechanism, in which the Goldstone bosons are eliminated and the gauge field acquire a new polarization. But in this construction, when I look at this quantity, which is called delta rho, the deviation from 1 of the ratio mw squared divided by mz squared cosine w squared, where the cosine is a mixing angle between the two U1s that I have in the construction, the one that identify the photon, the massless state, find that this quantity is equal to minus twice CT. Now, experimentally, we know that this ratio is equal to 1 at a very, very good approximation. So the first result is that when I do a most general construction of electroweak symmetry breaking, in principle, I would have two operators. One gives me the correct relation of the MW and MZ mass. The other operator gives me a contribution to delta rho, which we observe to be very small. So the first question is then why this coefficient Ct has to be very small. It's something of the order 10 to the minus 2, 10 to the minus 3. So it's something that looks like a loop contribution and not a tree-level contribution. So in order to understand why that operator is absent, we have to look a little bit into what are the symmetry properties of this term that I've introduced. So let me just look in what are the kinetic terms contained into these two terms that I've introduced. The first one, as I said, and you're probably very familiar with, is nothing else than the kinetic term of the three Goldstone bosons with the same coefficient. So this is the canonical kinetic term for these fields. Well, this term here has a projector in the third component, so it gives a contribution only to the third Goldstone boson. So that means that if I take for a moment the limit in which I turn off the gauge field, I go back to the global limit in which I set the gauge coupling constant to 0, what I find is that the first term has a larger global symmetry because you recognize this one as a global symmetry in which you can rotate the three Goldstone bosons. And the global symmetry of this term is an SU2 times SU2. Because I can, if I take just the global transformation, I can rotate the field sigma by an SU2 matrix to the left and a different SU2 matrix to the right. And in this case, this term is still invariant. It's invariant because the construction sigma dagger sigma eliminates the SU2 matrix to the left, and the trace eliminate the one to the right. This global symmetry, however, is not, this full SU2 times SU2 is not a symmetry of the vacuum. Because, remember, the vacuum was sigma equal to 1. So this means that the vacuum does not preserve a symmetry in which the two SU2 are different, but only the one in which the two SU2 are the same. So it breaks the SU2 left, let's call it times SU2 right, into the diagonal SU2. And you recognize that this is, if you study QCD, this is exactly the same story that happens in the chiral symmetry of QCD. But we're not talking about QCD here. We're looking at the Goldstone bosons of the electroweak sector. So this diagonal SU2 is a global symmetry of the sector that achieves the symmetry breaking. So I'm neglecting the gauge field, I'm neglecting any kind of standard model particle, but I'm just concentrating on the sector that breaks SU2. So it's described here in this effective theory but just by the Goldstone bosons. And this sector has an SU2 symmetry, which is a global symmetry, which is preserved by the vacuum. And this is called custodial symmetry. So what we have discovered is that those two terms that appear have a different symmetry property, one of which is invariant under custodial symmetry, while the other one is not. And the other one, we've also seen, its coefficient has to be very small. So clearly that means that an acceptable electroweak breaking sector has to preserve up to a certain level, up to a very good precision, this custodial symmetry. Actually, it's very easy to see why global SU2 ensures the relation that rho is equal to 1. Rho, I remind you, is this ratio mw squared divided by mz squared divided by cosine squared. Indeed, all you need to have is a global SU2 under which the generators of the SU2 left, the gauge SU2, transform as a triplet. And the second property is you need charge conservation. Once you have these two, then automatically you obtain the rho is equal to 1. Let's prove it. It's very simple. Let's look at the mass matrix of the neutral gauge bosons. So I have the W3 and the hypercharged gauge boson. The 1,1 entry is a W3 entry, but condition 1, the one that must exist an SU2 under which the three generators of the SU2 left are a triplet, requires that this entry has to be exactly the same as the mass term for the charge state. So it has to be NW squared, while the others, in principle, are arbitrary. Now, let's use hypothesis number 2, that is charge conservation. Charge conservation means that the photon has to be massless, meaning that this matrix must have determinant 0. Determinant 0 identifies the x, this parameter x, to be the square root of mw squared times y. Then I just define as mz squared the trace of this mass matrix, because the other eigenvalue is 0. So the trace has to be mz. The trace is mw squared plus y, so this fixes y. Now, if you look at what is the diagonalization angle of this matrix, and you're expressed in terms of x and y, you find that cosine square is exactly this ratio mw over mz squared. So this implies rho equal to 1. So the lesson is that we find a powerful constraint on the sector of electroweak braking. This sector must have a global custodial symmetry, which is preserved by the vacuum. Of course, this must be a symmetry only of an approximate symmetry only of the electroweak braking sector, but in general will be broken once you couple this sector with the standard model fields. So let's do this coupling. So first of all, we've learned that for the electroweak braking sector, I have to keep only this term at the leading order in a derivative expansion. Then I couple it with the standard model. The standard model, I define the standard model. See, I write it in this concise form. I have the gauge field and the fermion fields. And this fully describes the gauge interaction of the standard model. Of course, in this trace of FF, I mean the sum over the gluons, W, the Z, and the photon. And in this term, I mean the kinetic term, the covariant kinetic term for all the quarks and leptons that I have in the standard model. Then I have my electroweak braking sector, which is described a leading order in this expansion derivatives by this term. And then I can also couple the field sigma to the fermions in such a way. Now, let's look at this Lagrangian and comment it for a second. So the first line, as I said, is the standard model. And really, I think it summarizes very well this sublime beauty of the standard model, because we know that all forces, in spite of their very different phenomenological appearance, I mean, There's a big difference between electromagnetism acting at very large distances, strong interactions, binding the quarks and the gluons inside the nuclei, and the electroweak and the weak interactions. Nevertheless, they are all described exactly by the same symmetry principle. So I think this first line summarizes the beauty and the strength of the Standard Model, and it is reflected in the robustness of the theory, the sense that I cannot deform the interaction of the quarks and the leptons with the gluons and the gauge fields, because that interaction is completely fixed by the symmetry properties. I just need 3 numbers, the gauge coupling constant, and everything else is fully determined. So this robustness translates into a great predictivity of the theory, and of course also elegance of the theory, because it's fully determined by a symmetry principle. And it is really the richness of the gauge symmetry which is the secret for the complexity of the real world emerging out of the simplicity of the fundamental principle. Because I think it's really astonishing how just out from a simple principle you can get the complexity of the world that we observe, which has phenomena which are completely different. And my view, really the secret is the richness, because if you look at the 3 factors of the gauge symmetry in the Standard Model are, from the mathematical point of view, perfectly identical, and yet they give rise to a physics which is totally different. The second line, instead, describes the poor understanding that we have of the electroweak breaking sector. So in the case, when I replace here sigma with 1, its background value, as you see, I obtain the masses of the gauge bosons from this term and the masses of the fermions. What are these field sigma? Well, as you know very well, those Goldstone boson can be reinterpreted as the longitudinal components of the gauge bosons. And this lies in what's the so-called equivalence theorem, which shows that up to, so in the high energy limit, the Goldstone bosons can be identified with the longitudinal polarization of the W and the Z, in the sense that if I take any amplitude of this field, the 2 amplitudes are the same up to terms of order mv squared over E squared. So if I compute a process at energies which are larger than the mass of the gauge bosons, I can use either degrees of freedom. And this is, of course, the idea behind it is the Higgs mechanism. So this is now my Lagrangian that describes the full world that I know. Actually, this was describing the full world before 2012, because before 2 years ago, this Lagrangian was perfectly adequate to describe any process that we knew in particle physics. Notice that this Lagrangian is gauge invariant. There is a gauge symmetry. There is an exact gauge symmetry. It's just simply it's non-linearly realized, because this field sigma realizes it in a non-linear way. And also notice that once I couple this field sigma with the gauge interactions here and with the fermions, I'm breaking the custodial symmetry, which was valid just in the kinetic term of the field sigma. And it turns out that I'm breaking it by terms proportional to G prime, which is the gauge coupling constant of the U1 hypercharge, and proportional to the difference of the Yukawa of the up and the down sector. But these are small effects, meaning that the delta rho will be generated only at loop levels. So this is consistent with the observation. Also, notice that this Lagrangian shows you that the phenomenon of supersymmetry, of spontaneous symmetry breaking was established even before the Higgs discovery. And this is because the gauge structure of the interactions, in particular trilinear couplings, gauge coupling like photon WW or ZWW, have already been tested accurately at previous colliders, particularly LAP, but also partly the tevatron. And also the longitudinal polarization of the W and the Z were already proved to exist. On the other hand, we knew that the gauge symmetry is not manifest in the mass spectrum, because the W and the Z and the photon are not mass degenerate, so they're not in a mass degenerate multiplet. So in other words, what we have seen is that the propagating particles do not share the full symmetry of the interaction. But this is exactly the essence of the idea of spontaneous symmetry breaking. So spontaneous symmetry breaking was already established. But then why is this Lagrangian the end of the story? Well, of course, even before 2012, every theoretical physicist on the planet knew that this could not be the full story. This could not be the final answer. And the reason is that this is an effective theory, and it's with a perturbative expansion, which is valid up to a certain energy. And because, if I go to an energy which is larger than 4 pi v, what happens is that the higher derivative term become more and more important, and when I reach this point, then there's no expansion valid anymore because any term is as important as anyone else. So there's no perturbative expansion for energies larger than 4 pi v, which turns out to be about 3 TeV. Notice also that the weakness of the gauge interaction play an important role here, because the fact that we have a window in which we have a validity of the perturbative expansion of the low energy effective theory and a validity of the equivalence theorem is because of the weakness of weak interaction. Because remember that in order for the equivalence theorem to hold, you need to work at energy larger than MW. And in order to have a perturbative expansion, you need to be at an energy which is less than 8 pi MW divided by G. MW divided G is V, okay, up to a number. So if G is order 4 pi, then this interval shrinked. As I said, this theory must fail, and we see explicitly. For instance, let me just take the leading derivative term and then expand it in powers of fields now. And so this was a leading term, and I expanded in powers of fields. The first term is exactly the canonical kinetic term for the Goldstone bosons. And then I'm getting from nonlinearities some interaction of the Goldstone bosons. And because of the equivalence theorem, I can interpret this interaction of the Goldstone boson as scattering of the longitudinal components of the gauge bosons. And this amplitude, when I compute it, grows with the energy. S and T are the Mandelstam parameters, so they parameterize the energy. S is incoming energy, if you wish, the center of mass energy of the system, divided by V squared, where V is a typical energy. So you see that if I go to higher and higher energy, at a certain point, the perturbative unitarity fails, because this amplitude becomes much larger than one in the appropriate units. So this shows that necessarily, before that scale, something must happen. Something must happen. Either some new degrees of freedom enter the game and modify the theory, or I'm just entering a strongly interacting regime, and so I have new kind of dynamics at 4 pi v. So this meant that that there was an unescapable discovery at the LHC, as we all theorists were saying, although some experimentalists were incredulous. Now, the question is, what could this new physics be? Well, let me just do a simple example. Let's take one gauge singlet scalar field, and I couple it to the electroweak braking sector in a generic way. So I take my leading two derivative term describing the dynamics of electroweak braking, and then I couple it with linearly or with a bilinear and so on, with arbitrary coefficients. Now, as we saw, this WW amplitude grows with energy with S. If I now include this scalar field, I have a new contribution, which is exchange of this scalar, and this will give me this term, which is proportional to A squared, where A parameterizes the coupling of H to this arbitrary sector of the Goldstone bosons. It's clear that the growth, the power growth in the amplitude is killed for a specific value of A. So if I choose A squared equal to 1, see that the leading term in the large S regime exactly cancel between these two contributions, and then I am getting a constant value of the amplitude. Okay, so this means that my theory, if I want to have the scalar to restore perturbative unitarity, I have to fix this value equal to 1. Of course, this is not the end of the story, because although I've cured the elastic channel of the WW, the introduction of this new scalar will introduce other other amplitudes that grow in the high energy domain. So in particular, the production of two of these scalars will have an amplitude which grows with S again, which is, there is one contribution proportional to A squared. A, remember, is a linear coupling of this. But then I also have a contribution coming from the bilinear coupling, which is B. So now, if I choose A squared equal to B, I can cancel this. And I can continue this game forever. And then I can fix all the coefficients in such a way that channel by channel, this is canceled. Of course, one can look at it in a smarter way by doing an ultraviolet completion of the theory in which this growth of the amplitude is automatically cancelled. And the simplest way is to combine this scalar H with the Goldstone field chi in order to form an SU2 doublet, gauge SU2 doublet. And the construction is the following. You multiply this field sigma by a vector that has one component, V plus H, where H was that field. Now, it's a simple exercise now to see what happens to the two-derivative term of this field when I expand it in H and chi. What I find is that I am obtaining canonical kinetic term for all the fields and an interaction between H and the field sigma, which is exactly of the form before, with the coefficients now fixed, and they are fixed in such a way that A equal to B equal to 1. So I'm obtaining, by this construction, exactly the properties that restore perturbative unitarity. There's more to this. Now, let's look at this theory. So I've constructed this theory out of this doublet field H. So my Lagrangian will contain a kinetic term and a potential. The potential will have, in general, a quadratic, in terms of H dagger H and H dagger H squared. And I can write it in a compact way in this way. Now, this theory has a global symmetry. Let's look at it, because if I write this doublet H in terms of its real components, so I'm writing this, this is a complex doublet containing 4 degrees of freedom, and I can write as phi 1 plus I phi 2 plus I phi 4, phi 3 plus I phi 4. Now, the invariant H dagger H is just this combination. And this combination obviously has an SO4 symmetry, which I can rotate these 4 fields in an orthogonal way. These are real fields. SO4 is isomorphic to SU2 times SU2. The vacuum, H dagger H, give one non-zero value to one of these fields. So clearly breaks the SO4 into the SO3, which is isomorphic to SU2. So you see that this is exactly as the SU2 times SU2 global invariance, which is then spontaneously broken at the vacuum into an SU2. And this SU2 plays the role of a custodial symmetry. So you see what the construction that I did. I started with a fully generic sector of electroweak breaking. I did not want to specify at all. That sector could have been some weakly interacting sector, including the Higgs, but it could have been some strong interactions or whatever. Okay? There was the most general construction. But then I started to use experimental information. Out of that construction, I was nailed because I found out that because of the information on delta rho, I needed to have a global symmetry, which was this custodial symmetry. Then what I found out is that that effective theory had a limited validity, and in order to go beyond the perturbative limit, I had to include other degrees of freedom. And these degrees of freedom correspond exactly to the construction of an SU2 doublet, which you recognize as a Higgs field. So you see, as I've been narrowed down exactly into the formulation of the Higgs field just by generic argument. Of course, this custodial symmetry is broken once I couple this Higgs field to the rest of the theory, and in the standard model, this delta rho is computable in terms of m top and b mass, and also there are other contributions. This is a leading effect. And once I compare it with data, I find this. So let me explain. This y-axis is this parameter t, which is as a different definition of what I was calling it delta rho. There is a reason why phenomenologists change the notation, but I won't enter into that. This parameter is what is called S, essentially describes the effect of Z photon mixing coming from higher dimensional operators. But anyway, is a parameter that describes the effect of possible new physics beyond the standard model. And you see that the result, the standard model prediction, which is here, is just perfectly inside the experimental ellipses. And if I would remove the Higgs from the theory, I would move along this line and I would go against data. Actually, maybe I'll postpone this discussion to another lecture, but the Higgs field, the coupling of the Higgs field to the fermions have also special properties which are very delicate, and they are necessary to satisfy the experimental data. So, a priori, there was really no unique solution to the electroweak breaking sector. But experimental data show that the solution to the problem must be either the Higgs boson or something that looks tremendously similar to the Higgs boson. And so this is now the completion of the Lagrangian that I was showing before in terms of Higgs doublet. And it's fair to say that, that this is by far the simplest solution that I can imagine. But yet this solution, as we will see, is not very satisfying because it leaves too many unresolved questions. Maybe I'll pause here for 5 minutes because this is a good moment to break, and then I will continue.